Hi, I am Corinne and I will present ResDepth, a simple yet highly effective method to use deep networks for high-quality dense surface reconstruction. Conventional stereo methods produce passable reconstructions of a scene but may suffer from local biases and errors. In this work, we propose a residual learning approach to complement existing stereo methods rather than learning the entire stereo reconstruction in an end-to-end manner. The idea is simple. First, obtain an initial, approximate reconstruction with your favorite stereo matcher. Then, refine it by predicting a residual correction for every height value with a deep network. Our network is guided by both the approximate surface and the images, so it can exploit both alignment errors between the images and correlations between intensity and depth patterns. In this way, it can, for instance, reconstruct crisp crease edges and discontinuities and align them with contrast edges in the images. Our full model is based on stereo guidance, but we also investigate residual reconstruction with less information. It turns out that a single image already greatly improves over the initial surface model produced with state-of-the-art dense surface reconstruction, and stereo guidance brings further improvements. Our method starts from images with overlapping fields of view and known camera poses. We compute an initial coarse reconstruction of the observed scene and represent it as a 2D elevation map. Next, we select two input images and map them to the same image coordinate system via the initial surface model to obtain pixel-wise alignment. In the special case of aerial or satellite stereo, this corresponds to auto-rectification of the two images. With the initial reconstruction and the warped views as input, our network is trained to regress a height correction for every pixel, which is added to the initial height. In this way, the network acts as a learned prior for both the 3D surface and for its alignment with the 2D image structure. If the initial reconstruction were perfect, the rewarped images would be maximally photoconsistent with each other, and 2D image shapes would perfectly align with 3D surface shapes. Hence, disparities between the images and misalignments between each image and the elevation model provide a signal to improve the surface. Our network is a standard Unet architecture without any special modifications. We train it in a fully supervised manner by minimizing the L1 loss with respect to ground truth elevation maps. An alternative interpretation of our method is as a learned filter for enhancing depth maps guided by the original image content. This leads to the question how much each input channel contributes to the refined depth and whether all inputs are indeed needed for the refinement. We start from our full model based on stereo guidance, which we refer to as ResDepth stereo, and construct several baselines that ignore some of the input channels but are otherwise identical. In particular, we keep the network architecture fixed and train each variant using the same training data and settings. The first baseline, ResDepth mono, receives only a single image as guidance. Therefore, the network has no access to stereo disparities, but can still use monocular image information such as the location of image edges to refine the depth. The next baseline, ResDepth 0, does not leverage any image information. The network merely learns a prior on the structure of depth maps and corrects unlikely configuration of depth values without conditioning on any image evidence. Furthermore, we formulate a variant without the initial depth map, such that the network must learn to reconstruct the 3D surface directly from the two imperfectly rectified images. Finally, we also test an iterative variant of our full model. ResDepth stereo iter uses the output depth of ResDepth stereo as input, warps the input images with the new improved depth map, and trains another ResDepth stereo network to further reduce the remaining smaller depth errors. Our main application is large-scale urban 3D modeling from high-resolution satellite images. In our experiments, we use WorldView 2 and WorldView 3 images acquired over Zurich and generate an initial digital elevation model using a state-of-the-art satellite stereo pipeline. We then train ResDepth to upgrade that initial surface model. As supervision, we use elevation maps rendered from the publicly available CAD/CD model of Zurich. Note that this model does not include vegetation. Consequently, ResDepth implicitly learns to filter out trees and bushes present in the initial model. As a second test in a different domain, we also evaluate ResDepth on the close-range ETH3D benchmark dataset, where we run our approach with depth maps instead of elevation maps. Let's have a look at how well ResDepth performs on the satellite data. This is the initial reconstruction color-coded by elevation. It is rather noisy, as one would expect for an urban model derived from satellite data. ResDepth greatly reduces the noise and removes outliers due to matching errors. The refined digital elevation model is geometrically more accurate and detailed. Building shapes become crisper throughout the entire scene, and additional roof details emerge that were missing in the initial reconstruction. This example shows a qualitative comparison of the different network variants. As expected, ResDepth 0 without any image guidance mostly acts as a context-aware intelligent smoothing filter. Notably, it is already much better than the median-filtered initial model. Yet building outlines remain somewhat wobbly, and details missed by the original stereo matcher cannot be retrieved. ResDepth Mono already works surprisingly well. Even without stereo guidance, substructures on roofs start to emerge that were not visible in the input model, and straight lines and rectangular footprints are more faithfully reproduced. Adding a second image further improves the refinement. ResDepth Stereo, and even more its iterative variant, are able to further sharpen and straighten building outlines and to reconstruct thin structures. They yield visibly crisper and more detailed 3D geometry, and even recover additional details that were missing in the input surface, such as, for example, small dormers or the sawtooth structure of this roof. Our evaluation also shows significant quantitative improvements. Our best model achieves a final median absolute error of about 50 centimeters, about the pixel size of the input images, and a mean absolute error of about 1 meter. In summary, our learned residual stereo reconstruction approach yields geometrically detailed, accurate, and complete reconstructions at large scale and reduces the errors of state-of-the-art multi-view stereo reconstruction systems by more than 50%. For further experiments with satellite images, as well as results on the ETH3D dataset, please check out our paper. Thank you for watching.